Op-amps are linear circuits, so long as you don't saturate the output to the power rails. And a linear circuit means we can use the principle of superposition to actually analyze them. So I'll give you an example of using that here. So remember, in superposition, what we do is we choose each of the voltage sources in turn. So here we have 2 voltage sources. And then we turn off the other sources and create kind of like a partial circuit. I guess the superposition part 1 is to keep the 1.2 volt source and turn off the 4 volt source. So if we actually do that, then what is the circuit that we would end up with? So if I turn off the 4 volt source, turning off a voltage source means setting the voltage across it to 0. So 0 volts means a short circuit. So I am kind of thinking to myself, all right, well, what is that circuit going to look like here at this non-inverting terminal? Well, there'll be the 4 kilo ohm resistor and there'll be an 8 kilo ohm resistor, and both of those are just going to pull to ground. Sorry, this horrible squiggle here is a resistor. So 4 kilo ohm resistor and 8 kilo ohm resistor, and both of those are just pulled to ground, and there's no voltage sources here anywhere. So the voltage at that terminal must be 0, right? No current flows. No current flows in. There's no driving source to supply voltage. It's not a voltage divider. There's basically 0 volts. So in this case, there's 0 volts at that non-inverting terminal. So we have 0 volts at VP, so voltage at the non-inverting terminal. So what does that leave us with? Well, it leaves us with an inverting amplifier circuit. Right? It leaves us with 1.2 volt source, 10k resistor through our circuit. We have it grounded at the non-inverting terminal, and we have a 50 kilo ohm resistor, and that's it, right? That is an inverting amplifier circuit. So this is an inverting amplifier, and we know the behavior of an inverting amplifier. So we know that the output voltage, let's call it V0 prime, because this is only a partial contribution to V0. So we know that V0 prime is our input voltage, which is 1.2, multiplied by a negative gain, and the gain is going to be feedback resistance, which is 50k, divided by source resistance, which is 10k. So that will end up being negative 1.2 multiplied by 5, which would be 6. Negative 6 volts. Okay, so that's the contribution due to the first source. So then we'll have a look at the contribution due to the other source. So in this example, we keep the 4 volt source and turn off the 1.2 volt source. So let's redraw our circuit and make those changes to it. So I'm just going to copy it down the page a little bit, and then we'll redraw it with these modifications. So we're keeping the 4 volt source, we're turning off this 1.2 volt source. So that means we set it to 0 volts. 0 volts means just a short circuit across the terminal there. Okay, so what do we have here? Well, this is pretty much a non-inverting amplifier circuit. So we have the standard kind of feedback path, which is this bit that you see here, and we have a voltage that is connected to the non-inverting terminal. So this is a non-inverting amplifier circuit. This is a non-inverting amplifier. The only thing that's a little bit tricky is we have to figure out, well, what voltage actually arrives at the terminal VP. Fortunately, that's fairly easy to calculate, right? It's just a voltage divider. So it is 4 volts times 8 kilo ohms divided by 4 kilo ohms plus 8 kilo ohms. So we just get out our calculator and we multiply out. So 4 by 8,000 divided by 4,000 plus 8,000 is 2.6667, so 2 2/3 volts. Okay, now we can use our knowledge of the non-inverting amplifier. So the output for a non-inverting amplifier is 1 plus RF over RS times our input, VI. Now our input in this case is VP, so actually I'm going to write just VP directly, times VP. Okay, we have some numbers here, so RF is 10 kilo ohms, RF is 50 kilo ohms divided by 10 kilo ohms times 2.6667. So we can calculate that. So the gain is going to be 1 plus 5, 6. So it's 6 by 2.6667, which is 6 times 2. Is 16 volts. And I guess I should call this V0 double prime, because this is actually the kind of second sort of partial contribution. So this is V0 double prime here on my circuit. So this is the second kind of partial contribution due to our superposition. So therefore, by superposition, our total output voltage V0 is the sum of the individual ones. So our first one, V0 prime, was minus 6, and V0 double prime is 16. So we wind up at 10 volts as our final answer here. So the method of superposition allows us to analyze different parts of our op-amp circuit at a time, and it will apply so long as the op-amp operates as a linear circuit. So it's a linear circuit so long as the output voltage does not actually hit your supply rails. So we didn't label supply rails here on this circuit, the assumption being that our output voltage lies within this range, and if that's true, it's linear and we can use superposition.